Once again, a very good morning to all of you watching my lecture tutorials, and I'm back with lecture number 21 of operating systems. So let us start. As in today's lecture, we are going to see the very important concept of operating system that is called thrashing and allocation of frames. So stay tuned with me as I'm going to cover up some more important concepts in today's lecture. So let us start with the lecture today. So this is a topic, thrashing and allocation of frames. So in last lectures, we have already seen some of the concepts like the concepts of page replacement. Why do we need to have replacement of page? We have seen LRU page replacement algorithm, and there were other algorithms as well that we have seen, but these are the two most common algorithms that we normally use for the page replacement purpose. So these are the two algorithms that we are going to see. And then the objectives of today's lecture would be to know what exactly is thrashing and what are the concepts of allocation of frames. So let us begin with allocation of frames in operating system. Right. So see, basically an important aspect of operating system is virtual memory. Right. It is implemented using demand paging. We have seen demand paging earlier when we were doing non-contiguous allocation of memory, right? So demand paging necessitates the development of page replacement algorithm and a frame allocation algorithm. So, the frame allocation algorithms are used if you have, multiple processes. It helps decide how many frames to allocate to each process. So there are various constraints to the strategies for the allocation of frames. First, you cannot allocate more than the total number of available frames. Obviously, if you have, let's say if you have 25 frames, then this is not possible to allocate 26 frames to your different processes. The limitation is just of 25. So if you have 25 frames, you can allocate only 25. If you have 20 frames, you can allocate 20 frames. So this is what we can do. Now, at least a minimum number of frames should be allocated to each process, right? Now, this constraint is supported by two reasons. What? The first reason is, as less number of frames are allocated, there is an increase in the page fault ratio, decreasing the performance of the execution of the process. Secondly, there should be enough frames to hold all the different pages that any single instruction can reference. Now, let us begin with some of the page allocation algorithms that we have. Going into that, let us say that each process needs minimum number of pages. Consider that we have a single OS which has got 128K of memory with page size of 1K. Now OS takes 35K, leaving 93 frames for the user process. Now the first 93 page faults would get free frames from the free name list, right? Now when the free frame list is exhausted, a page replacement algorithm is used to allocate the frame. What are the constraints? It cannot allocate more than the total number of available frames. Only a minimum number of frames that can be allocated, that is possible, right? Now, this number is defined by the instruction set architecture. As the number of frames allocated decreases the page fault, increases, obviously frames are decreasing and the page fault is increasing. Now, this actually what it does is it slows down the process execution. Now, we'll understand the algorithms related to allocation. Now, see, there are two algorithms which are commonly used to allocate frames to a process. Like the very first allocation is called equal allocation. So, in a system with X frames and Y processes, each process gets equal number of frames, that is X divided by Y. Now, for instance, if the system has 48 frames and 9 processes, each process will get 5 frames. So the 3 frames which are not allocated to any process can be used as a free frame buffer pool, which in case if a page will require the frames, it will be allocated to them. So this will be considered as a free pool list here. So the major disadvantage of this equal allocation is that in systems with processes of varying sizes, it does not make much sense to give each process equal frames, right? Obviously, we know this thing that it is not, we cannot, there are lot many processes which are of variable size, so it is not of any sense that we can allocate, equal number of frames to every process. Maybe it could be a condition where, one process can need more than that. So again, this is an important part here. So this creates a major disadvantage in allocation, right? Now, allocation of a large number of frames to a small process will eventually lead to the wastage of large number of allocated unused frame. Even this is a major number of problem, right? Now, the second algorithm that exists is of proportional allocation. Now, frames are allocated to each process according to the process size. For a process Pi of size Si, the number of allocated frame is Ai is equals to Si divided by S into M, where S is the sum of the sizes of all the processes and M is the number of frames in the system. For instance, in a system with 62 frames, if there is a process of 10 KB and another process of 127 KB, then the first process will be allocated 10 divided by 137 into 62, which is equals to 4 frames. And the other process will get 127 divided by 137 into 62, which is equals to 57 frames. So what is the advantage here? See, all the processes share the available frames according to their needs rather than equally. This seems to be more rational, right? Now, let us understand what is global versus local allocation. So, the number of frames allocated to a process can also dynamically change depending on whether you have used global replacement or local replacement for replacing pages in case of a page fault. Now, what is local replacement? When a process needs a page which is not in the memory, it can bring in the the new page and allocate it a frame from its own set of allocation frames only. Now, what is the advantage? The pages in memory for a particular process and the page fault ratio is affected by the paging behavior of only that process. There is a disadvantage also. What is the disadvantage? Now, a low priority process may hinder a high priority process by not making its frame available to the high priority process. So this is what exactly we call is a the local replacement. Now understand what is global replacement. You see, when a process needs a page which is not in the memory, it can bring in the new page and allocate it a frame from the set of all the frames. Even if that frame is currently allocated to some other process, that is, one process can take a frame from another. Now, what is the advantage here? See, it does not hinder the performance of processes and hence results in greater system throughput. Then the disadvantage is that the page ratio of a process cannot be solely controlled by the process itself. The pages in memory for a process depends on the paging behavior of other processes as well. So at the end, you see, when we're talking about allocation of frames, there were two important tasks in virtual memory management. One, a page replacement strategy, and a frame allocation strategy. So, when we talk about minimum number of frames, the absolute minimum number of frames that a process must be allocated is actually dependent on the system architecture and corresponds to the worst case scenario of the number of pages that could be touched by a single instruction. So, if an instruction and its operands span, a page boundary, then multiple pages would be needed just for the instruction patch. Now, memory references in an instruction touch more pages, and if those memory locations can span page boundaries, then multiple pages could be needed for the operand access also. Now, you see, the worst case involves indirect addressing, particularly when multiple levels of indirect addressings are allowed. Left unchecked, a pointer to a pointer to a pointer to a pointer to a, likewise it will go on in a continuation manner. It could, theoretically touch every page in the virtual address space in a single machine instruction, requiring every virtual page to be loaded into physical memory simultaneously. Now, for this reason, architectures place a limit, say 16, on the number of levels of indirection allowed in an instruction, which is enforced with a counter initialized to the limit and decremented with every level of indirection in an instruction. So if the counter reaches 0, then an excessive indirection trap occurs. This example would still require a minimum frame allocation of 17 per process. Now, what are the allocation algorithms? See, we have seen equal allocation, we have seen proportional allocation. Then there are variations on this proportional allocations as well, which could consider priority of processes rather than just their sizes. So obviously, all allocations fluctuate over time as the number of available free frames, like M, it fluctuates, and all are also subject to the constraints of minimum allocation. Now, if the minimum allocations cannot be met, then the processes must either be swapped out or not allowed to start until more free frames become available. This is what we call exactly is the allocation of frames. Now let us understand what is the next concept, which is called thrashing. So understand what exactly is thrashing. See, the virtual memory actually, it works by treating a portion of secondary storage, such as a computer hard disk, as an additional layer of the cache hierarchy. So virtual memory is notable for allowing processes to use more memory than is physically present in the main memory, and for enabling the virtual machines. Now, operating systems supporting virtual memory assign processes a virtual address space, and each process refers to addresses in its execution context by a so-called virtual address. Now, in order to access data such as code or variables at the address, the process must translate the address to physical address in a process known as virtual address translation. Now, in effect, physical main memory becomes a cache for virtual memory, which is in general stored on disk in memory pages. Now, programs are allocated a certain number of pages as needed by the operating system. Active memory pages exist in both RAM and on the secondary storage. So, inactive pages are removed from the cache and written to the disk when the main memory gets full. So if processes are utilizing all main memory and they need additional memory pages, basically a cascade of severe cache misses known as page faults will occur. So often it will lead to a noticeable lag in operating system responsiveness. This process, together with the futile, repetitive page swapping that occurs, are known as thrashing. So this frequently leads to high runaway CPU utilization actually that can grind the system to a halt. Now in modern computers, thrashing may occur in the paging system. If there is not sufficient physical memory or disk access time is overly long, or in input-output communication subsystems, especially in conflicts over internal bus access, right? Now, you see, depending on the configuration and algorithms involved, the throughput and latency of a system may degrade by multiple orders of magnitude. Thrashing is a state in which the CPU performs productive work less and swapping more. So, the overall memory access time may increase since the higher level memory is only as fast as the next lower level in the memory hierarchy. Now the CPU is busy in swapping pages so much that it can not respond to users' program and interrupts as much as required. So thrashing occurs when there are too many pages in memory and each page refers to another page. So the real memory shortens in capacity to have all the pages in it. So it uses virtual memory. So, thrashing occurs when there are too many pages in memory and each page actually refers to another page. So, the real memory shortens in capacity to have all the pages in it. So, it uses virtual memory. When each page in execution demands that page that is not in currently, in real memory, like random access memory, it places some more, pages on the virtual memory and it adjusts the required page on RAM. Now, if the CPU is too busy in doing this task, thrashing occurs. Now, what exactly are the causes? So, in virtual memory systems, thrashing may be caused by programs or workloads that present insufficient locality of reference. Right. Now, what is locality of reference? Let us understand. The program and data references within a process tends to cluster. So only a few pieces of a process will be needed over a short period of time, possibly to make intelligent guesses about which pieces will be needed in the future. So this suggests that the virtual memory may work efficiently. Right. So if the working set of a program or a workload cannot be effectively held within physical memory, then constant data swapping, that is thrashing, it may occur. So the term was first used during the tape operating system days to describe the sound the tapes made when data was being rapidly written to any rate. A worst case scenario of this sort on the IBM System 370 series mainframe computer would be an execute instruction crossing a page boundary that points to a move instruction itself, also crossing a page boundary, itself pointing to a source and a target that each cross page boundaries. So the total number of pages thus involved in this particular instruction is 8, and all 8 pages must be simultaneously present in memory. If any one of the 8 pages cannot be swapped in, for example, to make room for any of the other pages, then the instructions will fault, and every attempt to restart it will fall or fail until all 8 pages can be swapped in. can be the other issues? Thrashing is best known in the context of memory and storage, but analogous phenomena occur for other resources, including cache thrashing, where main memory is accessed in a pattern that leads to multiple main memory locations competing for the same cache lines, resulting in excessive cache misses. Now, this is most problematic for caches that have no associativity. Now, TLB thrashing, where the translation book aside buffer acting as a cache for the memory management unit or MMU, which translates virtual address to physical address, is too small for the working set of pages. TLB thrashing can occur even if the instruction cache or data cache thrashing are not occurring, because these are cached in different sizes. Instructions and data are cached in small blocks, cached lines, not entire pages, but address lookup is done at the page level. Thus, even if the code and data working sets fit into caching, if the working sets are fragmented across many pages, the virtual address working set may not fit into the TLB, causing TLB thrashing. Now, what is heap thrashing? Frequent garbage collection due to failure to allocate memory for an object, due to insufficient free memory or insufficient contiguous free memory, due to memory fragmentation, is referred to as heap thrashing. Now, what is process thrashing? A similar kind of phenomena which occurs for a processes when the process working set cannot be co-scheduled. So, not all interactive processes are scheduled to run at the same time. They experience process thrashing due to being repeatedly scheduled and unscheduled, progressing only slowly. Here you can see concept that we have seen, that swapping out of a piece of a process just before that piece is needed. So the processor spends most of its time while swapping pieces rather than executing user instruction. So we have seen that this is called thrashing. And if a process does not have enough pages, the page fault rate is very high. So this leads to low CPU utilization. Operating system at this time thinks that it needs to increase the degree of multi-programming. Now another process is added to the system. A process is busy swapping pages in and out. Now this high paging activity is called thrashing, and more paging and less CPU utilization. Now what could be the disadvantages? Increases the thrashing, it increases the degree of multi-programming. System throughput decreases in this case, and the page fault rate increases. Then there are effective access time which increases, and this phenomena is shown in the next slide that I'm going to show you. This phenomena that you can see. See, we can reduce the effect of thrashing by using the local replacement algorithm. Now, to prevent thrashing, provide as many frames as it needs, and to know the number of frames using working set strategy. Now, why does paging work? Because there's a locality model, and the process migrates from one locality to another. Now, localities, they may overlap. And why does thrashing occur? The size of locality, it is greater than the total memory size. me see locality in a memory reference pattern. So now I hope that in today's lecture everything is clear to all of you. So let us move on to the MCQ part and understand what you have gained in this. So this is question number 1 and 2 that you need to answer. Quickly go through it and try to answer. This question is already clear to all of you. Let me take you to the second and third question that we have. These are the two questions that we will need to attempt. The maximum number of frames per process is defined by. And the second question comes. Here I'm going to present another MCQ to you. Let us start to solve this. Try to solve this question quickly. Let me take you to the next questions. Now, when a page fault occurs before an executing instruction is complete, if the instruction must be restarted, the instruction must be ignored, the instruction must be completed, ignoring the page fault, none of the above mentioned. We have already seen all these things, then I think we will be able to answer all the questions correctly. Let me take you to the next set of questions. The algorithm in which we split m frames among n processes to give everyone an equal share, like m divided by n frame, it is known as proportional allocation algorithm, equal allocation algorithm, split allocation algorithm, or none of the above mentioned. Try to answer it quickly. Now let me take you to the next set of questions. The replacement generally results in greater system throughput. Is it a local or global or universal or a public? Then the next question says that one problem with a global replacement algorithm is that it is very expensive. Many frames can be allocated to a process. Only a few frames can be allocated to a process. A process cannot control its own page fault rate. So with this, I hope you were able to answer all the questions correctly. So this is what we had regarding thrashing and allocation of fields. To learn some more important concept about operating system, keep on watching and keep on learning with these operating system tutorials. Thank you so much. Stay tuned, and if you have any kind of problem related to the topics, you can very well give your comments on the comment section box so that I can answer your queries. Thank you so much. Thank you for being here.